Assalamualaikum. So for our name for project is FEA analysis of mountain bike frame. So this is our group member. The first one is Muhammad Arif Hakim bin Masizam, and the second one is Muhammad Nur Haziq bin Abdul Halid, and the third one is Danish Haikal bin Nazri, and the last one is Azfar Zakwan bin Ash'ari. Assalamualaikum, my name is Danish Haikal bin Nazri. So for project background, bicycle construct as mountains are durable, have good traction and are well controlled on rugged off-roads. They are subject to extreme loads including impacts, jumps, rough riding, rough surface, and are very ruggedly built, which puts them under considerable mechanical stress, torsional stress, bending and shock loading. The needs to attain both excellent structural integrity and strike a balance between weight, stiffness and compliance has emerged as a major issue in the design of mountain bike frames. Conventionally, designers use physical tests, although it is time consuming and expensive. Nowadays, finite element analysis (FEA) gives a more efficient and correct way to simulate real-life terrain and evaluate the performance of frames. With FEA, engineers are able to analyze how a mountain bike frame will be affected by dynamic impact, repetitive loading and torsional loading, determine the area of the highest stress and optimize the design to be as strong, fatigue resistant and ride quality as possible. This project is aimed at studying a mountain bike frame under various off-road loading with FEA methodology. For problem statement, the mountain bicycles are designed to be durable, controllable and off-road bicycles. They have tough loading conditions of trail, drops, rock hits and uneven terrain torsional loads when used. Poor frame design provides too much flex, fatigue breakdown, low stability or even major structural damage. The design based on trial and error approach is ineffective and may not provide accurate estimation on trail stress in the real world. Hence, such a methodological pattern as finite element analysis (FEA) will play an essential role in simulating the structural behavior of the frame relation to real off-road conditions. This project addresses the need to analyze a mountain bike frame using FEA to identify critical stress regions, assess deformation, and ensure that the frame design meets both safety and performance standards. For objective, first one is to design a 3D model of a bicycle frame based on literature research in SolidWorks. The second one is to perform finite element analysis (FEA) under 3 different loading conditions. The third one is to identify critical stress and deformation area that may lead to failure. The last one is to determine the most critical loading case based on safety factor. For scope, this research focuses on modeling and analyzing a bicycle frame using SolidWorks and ANSYS. They create a detailed 3D model in SolidWorks 2019, selecting aluminum alloy 6061 for its strength and weldability. The SolidWorks model was then imported into ANSYS for static structural analysis under 5 different loading conditions, such as static start-up, rear wheel braking, steady-state pedaling, vertical impact, and horizontal impact. For each case, they measured total deformation, von Mises stress, and elastic strain to assess the frame structural impact. Additionally, the safety analysis ensured the compute stresses were below allowable material limits, adhering to safety standards. The study is limited to static analysis and relies solely on visual testing without physical models. For methodology, the first one that we use is SolidWorks. SolidWorks is a powerful 3D CAD software used by engineers and designers for product design, simulation and management. It offers tools for mechanical design, product simulation and data management, and technical communication, helping users develop products from concept to production. Its intuitive interface makes it a popular choice across various industries. The second one is ANSYS. ANSYS is a multinational company providing engineering simulation for software (CAE) tools. It allows engineers to create virtual prototypes and simulate designs under real-world conditions, analyzing structural, fluid, electromagnetic, and multiphysics behavior. This optimized design reduces physical prototypes accelerate development, and improve product reliability.
Assalamualaikum, I am Asfar and I want to talk about our project geometry. So for the top tube, the dimension is 550 mm and the diameter is 50 mm. For mid tube, the dimension is 550 mm and the diameter is 50 mm. So the bottom tube, the dimension is 630.45 mm and the diameter is 50 mm. So for the bottom bracket shell, dimension is 60 mm and the diameter is 40 mm. For 6 length, the dimension is 530 mm and the diameter is 20 mm. And for the last part is head tube, 200 mm for the dimension and 33.7 mm for the diameter. So for our material selection for this analysis, aluminium alloy 6061 T6 was chosen for the entire bicycle frame due to its balance of strength, weight, cost, wearability and corrosion resistance. Consistent with industry standards and the journal article, linear elasticity was assumed for the analysis, valid for typical service load and factors like temperature, corrosion and fatigue were excluded to align with the journal scope. Material properties were directly sourced from the ANSYS Engineering Data Library. For the meshing, in ANSYS Workbench, a tetrahedral mesh with a uniform 5 mm size was generated for the bicycle frame, yielding approximately 32,507 nodes and 13,912 elements. This element type is ideal for complex geometries and the mesh quality was validated against ANSYS guidelines for skewness, aspect ratio and orthogonality, ensuring numerical stability and reliability for comparison with the journal reference. For boundary conditions, following the reference journal article, fixed supports were applied at both dropouts and the head tube of the bicycle frame. A vertical force of 813.94 Newton, simulating a rider and cycle dropping onto a rigid surface, was applied along the seat tube. The boundary conditions and loading configurations were chosen for consistency with prior research, allowing for valid comparisons and ensuring the numerical model's realistic response verified through mesh sensitivity checks. So for the solution, following the static structural analysis, the maximum von Mises stress and its location were extracted from ANSYS Mechanical to identify potential yielding. Total deformation and stress contour plots were generated to visually represent structural response, pinpointing stress concentrations and critical deformation areas. These plots were then compared qualitatively and quantitatively with the reference journal article for validation. So for the comparison, the vertical impact analysis results, specifically the maximum von Mises stress and total deformation, were compared to a reference journal study to validate the error. The simulated peak von Mises stress of 46.5 megapascal and the seat tube showed good agreement with the journal's 39.392 megapascal, with potential discrepancies due to tube diameter. Similarly, the maximum deformation of 0.047 mm closely aligned with the reference value of 0.10262 mm, with difference possibly from solver types or geometric modeling. Attempts were made to achieve a validation error of less than 20% using the journal's parameters without a given diameter.
Hello, Assalamualaikum. My name is Muhammad Hairul Kamil Masrizam. So today I will explain about the validation error. Validation confirms the simulation model's accuracy by comparing its outcome with reference data. Quantifying discrepancies as a validation error of 15.286%, which is within the acceptable 20% range, indicates that the simulation results are accurate and consistent with the data. Confirming the appropriateness, reliability of the numerical model and boundary conditions used is enhanced for predicting system behavior. Thus, the simulation is considered valid for further analysis or design optimization. The verification error result is which is in acceptable range below 5%. This indicates that the numerical model has been implemented correctly and that the simulation is solving the governing equations accurately. The low error confirms that the mesh quality, solver settings, and numerical methods used are appropriate, ensuring the reliability of the computational setup. 3 different loading conditions were designed by each group member to determine the highest maximum stress, with the boundary condition including steady-state pedaling, horizontal impact, and vertical impact, representing typical cycling scenarios. Steady-state pedaling simulated continuous riding force, while horizontal and vertical impact accounted for sudden obstacle or uneven terrain. By analyzing these conditions, the group aimed to identify the most critical stress points and ensure the structure's durability under varying loads. The findings from this analysis would not only highlight the most demanding loading condition, but also provide essential insights for optimizing the frame's design, material selection, and safety margins. Ultimately, this approach ensures that the bicycle could withstand everyday use conditions, durability, and rider safety. In the steady-state pedaling simulation, the bicycle frame is subjected to typical riding loads with its dropouts. A 700 Newton downward force is applied at the bottom bracket for pedaling, and a 200.6 Newton force at the head tube for handlebar loading. The resulting moderate maximum stress 30.358 MPa and deformation 0.10456 mm indicate the frame ability to withstand continuous pedaling, assessing its long-term durability under standard usage. The vertical impact test simulates landing force, fixing dropouts and the bottom of the head tube while applying a 980 Newton downward force at the seat tube. This scenario, while inducing stress, is less severe than horizontal impacts, which yield at max stress of 145.81 MPa and deformation of 6.3264 mm, indicating the frame's better absorption of vertical shocks. The result assess the seat stays and seat tubes' ability to withstand hard landings without permanent deformation, suggesting the frame is more resistant to downward force. However, repeated vertical impacts can lead to fatigue failure, especially at welded joints and thin wall sections. To ensure consistency with a reference study, field support were applied to the bicycle frame's dropouts and head tube. A static concentrated load of 200 Newton was applied at the bottom bracket and 700.4 Newton at the seat tube, simulating rider force during pedaling in vertically equilibrium state. These boundary conditions and loading configurations were chosen to align with the reference study, allowing any result deviations to be attributed to specific variables rather than boundary condition difference. Mesh sensitivity checks verified the numerical model's realistic response under these prescribed conditions. The safety factor analysis presented in the table evaluates the structural integrity of a component under 3 different loading conditions: steady state, vertical impact, and static startup. The component material has a constant yield strength of 259.2 MPa, and the safety factor for each case is calculated by dividing this yield strength by the maximum von Mises stress experienced in each scenario. Among the 3, the static start-up condition is the safest, with a safety factor of 14.523, indicating the component is significantly over-designed for this load. The steady-state condition has a moderate safety factor of 8.433, 488, also showing sufficient safety. However, the vertical impact load results in the highest stress and the lowest safety factor of 6.580, suggesting it is the most critical loading condition and the one that most closely approach the material strength limit.
Parameter change in the vertical impact. Parameter change in vertical impact is set on seat tube because vertical impact on the seat tube has a lower safety factor than steady state and static startup. The parameter change in the vertical impact simulation clearly show that the increasing parameter 1 at P1 improved the minimum safety factor significantly. Figure 4.0.2 is illustrate a parameter chart setup where the x-axis represent a design input. P1 is thickness and the y-axis represent the safety factor minimum P2 under the vertical impact. This configuration allows for visual analysis of how change in the input parameter affect the safety factor. With the current simulation result, P1 is 16.85, P2 is 11.682 include. Such charts are a vector for understanding the influence of the design modification on safety performance. Figure 4.0.3 is represent a parameter analysis table showing how a design input P1 from 13.5 mm to 16.85 mm influence the minimum safety factor under vertical impact. The data demonstrate that increasing P1 significantly improve the safety factor, change structural performance. For example, P1 of 13.5 mm yields a low safety factor of 1.4287, while 16.85 mm result is a high safety factor of 11.68. The table with the current design point retained is crucial for the design optimizing, increasing safety without over design. The graph shows the relationship between P1 and the parameter 1 in mm on the x-axis and P2 is safety factor minimum of the y-axis. The plot indicates that as a parameter 1 increase from about 30.5 mm to 16.7 mm, the minimum safety factor rises sharply from the sharp above 1 to over 12. The upward trend is a non-linear but constantly positive, suggesting that increasing P1 leads to a significant improvement in safety factor. This likely reflects a design sensitivity where increasing a critical dimension, thickness, or diameter greatly improve the structural safety, making the system more resistant to failure under load. The chart implies that optimizing P1 is an effective strategy for achieve a higher safety margins. For the conclusion, this finite element analysis successfully modeled and analyzed a 3D bicycle frame in SolidWorks and ANSYS under 3 load case, accurately determined areas of a maximum stress and total deformation to predict a structure behavior at a potential failure points using aluminum alloy 6061 for consistent material performance comparison. The FEA models validation error of 15.286% indicate fair equipment with a journal data, but a low verification error of 3.486% confirm the internal consistency and reliability of the numerical model and computational setup. The safety factor analysis show higher frame strength during a steady state pedaling and static startup, with the lowest safety factor observed under vertical impact. For the recommendation is based on this result, future work should aim at improving the FEA model to minimize more the validation error, which may involve a more intensive experimental-based material property validation or a more complicated joint behavior. It is also possible to consider using other aluminum alloy to composite, a material that may have a reduced weight at the same or better structure strength, especially in the vertical impact case. The possibility to investigate the optimized frame geometries, particularly in the regions that are marked as having high stress concentration in case of impact loads, may also result in the considerable design enhancement.